So there's 6 interconversions between the cell voltage, the equilibrium constant, and the free energy change. And I don't think it's worth doing all 6 of those, but maybe I'll give you a quick example of one. So perhaps we have an equation, and maybe we've built a cell, and I don't know, we've got ourselves a cell reaction that's like x2 positive plus 2y goes to give you x plus, I don't know, 2y positive. And maybe we've built the cell and we've got a cell voltage of, say, positive 0.10 volts. And it's a 2 electron transfer. And we want to know what the equilibrium constant is at, say, 25 degrees C. So we could go ahead and we could use this equation now. So we could say that, E cell standard is equal to RT over NF times by the natural log of K. Or if we wanted to, right, we could rearrange and we could say the natural log of K is equal to NF E cell over RT. And if we want the equilibrium constant, we have to anti-log. So that would be E to the power of NF E cell over RT. Okay, so now we're ready to go ahead and do this calculation. So we can calculate the equilibrium constant. So it would be E to the power of N. So that's the number of moles of electrons transferred. So that's why in all these videos, I've tried to write the number of electrons above the arrow. So that is 2, or if you like, 2 moles. The Faraday constant is 96,500 coulombs per mole. The cell voltage was positive 0.1. Okay, now we might think about units here. We saw earlier that the volt is equal to the joule per coulomb. So the voltage is essentially the amount of energy a coulomb of charge picks up as it goes between one point and the other. So we might write that as joules per coulomb maybe. Okay, and that is all divided by RT. Now, there's a couple of different R's kicking around in general chemistry. So since we're dealing with energies, we're almost certainly going to be dealing with the 8.3145 joules per mole Kelvin. And the temperature is in Kelvin, so 298.15, although we probably don't really need the 0.15 here. In terms of unit cancellation, so yuck. So Kelvin, Kelvin, per mole, joules, joules, coulombs, coulombs, and oh, you know what? That too should have just been a number, so that's kind of embarrassing. Let me go ahead and just delete that and pretend I never said that. So that is just a number. Okay, so now we've got no numbers at all. We've got no units at all. We just got a number. So the equilibrium constant then is E to the power of 7.785. Okay, actually, I probably can't really go past there, but I'm going to use the last answer on my calculator, so I don't want to round. And then I think that's going to be 2400. We might look at that and we might say, does that make sense? So, part of us might say, well, I don't know, what's a good equilibrium constant? But we've got a positive cell voltage, which means the reaction is favorable. And if it's a favorable reaction, it should have an equilibrium constant bigger than 1. And 1/10 of a volt is, I don't know, it's a little bit favorable. So this equilibrium constant's a little bit large. Some of these can be on the order of 10 to the 6, 10 to the 10, 10 to the 20. So it's favorable, not incredibly so, but pretty darn so. So it makes sense to me. So that's kind of cool, I think, that essentially by measuring the voltage of a cell, of a battery, you can in fact be calculating the equilibrium constant. So remember that lab we did with the iron thiocyanate, and we made all those solutions, and in the first part we made the one really concentrated, so it kicked the reaction to completion. We measured the color, and then the second part we used the color measure to calculate the concentration, and it took 3 hours. Well, imagine now you could have just built a battery, and you could just hooked it up, and you could have just used a voltmeter to measure the voltage, and bonk, you put the voltage in on your calculation, and you run it through here, and you get the answer. How much faster would that have been? Yeah, exactly. So that's why electrochemistry is cool. All right, good job.